So we often keep telling that databases typically store data as B plus trees on our disk. So actually, let's try to dig deeper and understand why B plus tree as a data structure is leveraged by databases to store data on the disk, right? So let's start. Okay. Um, let's start like this. Okay. So we typically have RAM wherein whatever has to be executed by the operating system, like whatever operation has to be done by the operating system, it brings it onto our RAM, which is our memory uh, storage, which is RAM is basically our memory storage for anything to be executed on the machine. The operating system brings it onto the RAM, and from here, it is brought into the processor. It is fetched into our CPU, where you have ALUs and other units which do the, you have registers which basically perform the algorithmic operations which are to be done. And then we typically have our hard disk or hard drive, as you may say it. So this is basically our hard disk. So we say that we often keep telling that the storage of my device is 256 GB or 1 TB in some cases, or 128 GB. What we essentially mean is that the storage in our hard disk is this much, and we say our RAM is 64 GB, or in our phones or in our laptops 8 GB. So this is basically our RAM is where it is bought. Anything to be executed in the machine is bought here. Okay, that's the basic concept. So typically when you do command S operation on your machine, that's when it gets to, anything gets stored on your hard disk, right? And it's fetched from the hard disk onto the RAM, and from the RAM it is brought into the CPU. Now, let's say we have a database wherein the data is stored in the form of tables, and inside the tables you have different columns where you can assign a fixed data type. If it's a relational database, let's say it's an int or a string or whatever it is, float, and you assign a fixed width to it while storing into the table. Now, let's actually try to explore why SQL databases store data in B plus trees, and even some non-relational databases actually leverage B plus tree to store data. Like for instance, MongoDB, it stores collections data on disk. Okay, let's start now. So let's take case A, wherein we have data which is stored sequentially in the form of a file, that is one after the other. So data is stored as a file, one after the other, row wise the data is stored, right? Okay, so if you look at our table structure in relational databases, then typically a table consists of multiple columns. We typically have a primary key, or a primary key which is typically an ID which is unique to that particular row or record. Okay, now, and whenever the data is inserted or stored in the database, it is ordered by the primary key. That is, it is sorted by the primary key. So I've inserted, let's say, record 1 with primary ID 2 and other details, 2 with 2 other details. Now let's say I have inserted record 4 with certain details, right? And if you typically look at any database, operations typically involve CRUD operations. Any database typically involves these 4 operations. You create, you read from the database, you update the database, and then you delete from the database. These are the typical operations that you would expect, right? Okay, now let's say I want to perform an update operation. I mean, I've inserted record 4, but now I want to insert somewhere here record 3. So is it that straightforward to insert record 3 onto our file? Basically, I have to open the file, append the row, in between. It's not that straightforward in a file. So what is the solution to update not update, sorry, actually I'm not as update. This is actually insert. I'm sorry, I want to insert row number 3 into the database, not update an existing record. So it's not an easy operation, right? So one of the solutions to actually do this is you create another temporary file, you open a file, and then you before one approaches, like before the element that you want to insert, you copy all of this into a separate file, insert this record, the one that you want to insert, and then you correspondingly add into this temporary file the other records that you want in the order 4 and so on and so forth. So this, if you look at this, this is a very expensive operation, right? I mean, it's basically like a linear search. You have to actually check whether it exists or not. If it doesn't exist, then insert it, and you have to basically keep on checking till the end, till the length of this file, right? So if you look at the time complexity, it is O of n, right? O of n is not a very efficient, it doesn't give, it's not that efficient in terms of efficiency performing operations, right? And also if you look at databases, we have one more operation called as range queries. So range query is also commonly used. And in basic so basically in range queries, what we essentially do is we specify the range. So that means give me all the rows which are present in this range. Let's say from id 1 to id 100, give me all these records between these in this range, right? And if you look at range query also, again it has to actually search where does index 1 start, but since it starts from 1, so it's a best case scenario, right? But what if give me records from 98 to 100, it has to do again O of n searches to actually reach. So we'll actually try to explore how B+trees are more efficient in terms of performing range queries and the other database operations. Okay, now let's actually start with, we leverage B+trees for storing data on the disk, and we'll even try to explore why don't we use B trees and rather why do we use B+trees. Okay, so if you typically look at the structure of a B+tree, let's take it as 2 elements, let's say 22 and let's say 200, and somewhere here you have some record stored, here some, I mean, let's typically say 300, and typically you have some record stored, right? So I mean, just don't go by the structure of the B tree, but here all the elements here are lesser than 22 and all the elements here are more than 300, and in between they are between 22 and 200. That's how the elements get stored, right? So even you can have one more. Actually, don't go by the structure of the B+tree, but go by the essence of what I'm trying to say, okay? Well, yeah. Now, let's say I want to perform different CRUD operations, okay? Different CRUD operations having B+tree as my data structure, which is leveraging B+tree as a data structure, and also range query that we have discussed. How does B+tree leverage range query to make our operations faster and efficient, right? Now let's say I want to search something, right? So in terms of searching something, it's way faster because I know if I want to search 19, I won't search these. I know that 19 is lesser than 22, so my search will be restricted only to this part. So in this case, the time complexity is obviously log of n, O of log n basically. That is my time complexity, because obviously it's much better than O of n. And yeah, I mean, if you want to perform range queries, let's say, it's even more efficient for B plus trees than B trees, because these B plus trees, they are connected internally. So so essentially, what do we mean by they are connected internally is they have pointers. Basically, the first element of a B plus tree node, it contains a pointer, and basically a pointer is nothing but it stores the uh, memory location. So let's say the memory location for this element is 1000. So it typically stores the offset of this one, that is, it stores this. So if anybody wants to search it, they know that the memory, so essentially the addresses are stored in hexadecimal, but for simplicity, let's take it as an integer, a number basically, right? It stores this. So that's how they are connected internally, and you can traverse through them. So if you want to perform a range query, let's say from 19 to 300, it's simply a traversal, right? So which saves our time a lot more. It's time wise, it's much more efficient than actually trying to search them. And also using your file systems, and also you have, and also depending on different databases that we have, like MySQL, Postgres, and whatever other databases that we use, they have different storage engines. And these storage engines, they basically allocate the B plus tree nodes on disk, and these are not stored in contiguous memory locations. They are stored as per the location of the storage engine and the OS. So yeah, I mean, that's one more point. And yeah, I mean, obviously, I mean, I was reading about why B plus trees are much more efficient for storing, why actually databases leverage B plus trees to store data. So this was the reason I found, and actually, if you dig deeper, there are many other reasons. So yeah, I mean, that's it from mine.